It is word on the street?
Yeah, you can pop up brain or whatever you want.
Well, you hold it anything you can pop. Rain up, like.
I don't know, I just heard that, so.
Well, if you do like, if you sneeze, you do this,
Yeah.
and then it might come out of your sinuses. I've had to pop my ears before. Not on purpose. It's pressure. Pressure builds up underneath the, you know?
I never heard that. I thought it was just that you would just pop a brain.
Never?
Never blocked your ears.
Yeah. Not on purpose. Oh, because all your sinus cavities are connected. That's why it could happen.
Oh.
That's why you sneeze really hard, you start to cry. You get like really, yeah, blow your nose really hard, you get like gross. Yeah.
Gross.
It's gross, but it's true. It's all connected.
Okay.
Okay. Now, you got several things. First, all face forward. The topic we're going to do today is actually very, very easy. The other class is a major success today. This topic is easy. You're going to see. It's not tough. Now, you're going to have to know one equation. That's it. Now, from that one equation, all you're going to do is solve for one variable. It's not five.
I know exactly what it is, too.
So, what we're going to do today is talk about energy and how it's conserved. Now, before I get into this, let's discuss what does it mean for something to be conserved? And that's tough to think about. Saved. Okay. Stored. I like stored. Okay, stored.
That's a biology.
Yeah, it is science. So when you hear conservation, think about this. If there's conservation of energy, it means that there's no energy that's being lost. It's conserved. So like, if you conserve your energy before a basketball game, you don't like run around and exert all this energy so you're tired, right? You're storing up that energy, or you're holding on to that energy. So conservation means that there's no change in energy, really. The overall energy never changes. So for example, if I were to take this remote and throw it across the room, it's got kinetic energy initially. It's also got potential energy because it's a certain elevation off the ground. That energy is not going to, just disappear. It's going to change. It's going to speed up, or it's going to slow down, or it's going to change height. So we're going to lose potential energy. Like yesterday's lab. Yesterday's lab was a perfect lead into this topic. And that's the reason we really started. Remember how the total energy was always constant? And either it was all potential, it was all kinetic, or it was like a little bit of mix. Good, both. That's the idea of today's lesson. That's all it is. Now, in yesterday's lab, we talked about a skater that was going back and forth, and he changed between potential and kinetic. Now, in this lesson, we're going to do that to begin. And toward the end of it, which is more toward tomorrow and Friday, we're going to really look at what happens if there's a spring involved also. How does that involve the problem? How does that affect the problem? In addition to that, what happens if there's some energy that's lost, friction? So, I take this book and I slide it across the floor. It starts with kinetic energy because it's moving, right? And then it stops. Where did all the kinetic energy go? It went into friction. It was that loss of energy due to friction and the heat between the book and the ground. So that when this book slides across the floor, if you picked it up right away and you're able to measure the temperature, it would be a little bit higher than it was beforehand. Because there is some sort of thermal energy loss. So when you rub your hands together, aren't you putting in kinetic energy? Motion?
Yeah.
Well, it's not going nowhere, it's going somewhere. It's dissipating. Dissipating means it's giving it off to the environment around you. So when you do this, the heat from your hands, and then you let go, the heat is actually being absorbed almost in a sense by the environment around you. So you're not losing energy, okay? It's just being transferred into another medium. So that's the idea of a lab. You are never losing energy. It's just that you start with potential, it goes down, it becomes kinetic. Then it goes back up, it becomes potential. And then kinetic, and then potential, and so forth and so on. Okay? Now, what we're going to do today is identify just situations that involve this and recognize the different forms of energy. All right. So first, whoops. Oh no. Okay, let's start with this side now. The first thing we're going to look at, and we're going to talk about, is the idea of what's called mechanical energy. And mechanical energy, just to write this down, is simply potential and kinetic energy. So mechanical energy is potential and kinetic. That's what we mean when we say mechanical energy. I'm going to orient the board real quick. So, for example, an object is on a cliff, right? And it's launched from the cliff with some initial velocity. So now it's got velocity and it's got height. So it's got kinetic energy because there's velocity, and it's got potential energy because there's height. So whenever we talk about mechanical, we mean potential and kinetic. Now, Tristan, there's examples like the skateboard example. When that skateboard was at the top of the ramp, it was all potential. So this went to 0 over here. Oops. The KE value, we could say, went to 0 in that example when the person was at the top of the skateboard ramp. Or when the person's at the bottom of the skateboard ramp, there's no height. So this would go to 0, so you'd have all kinetic. So you can have one or the other, or you can have both. But when I talk about mechanical energy, I mean either of them or both, depending on the scenario. Okay? So the idea here is this. There is conservation, which means that the amount of energy in the beginning is the same as the amount of energy
In the end.
in the end, right? In the end. That's what conservation means, it's constant. So here's what we're going to write. Here's our equation for this. And this is the only equation you really need to memorize. And that's what I'm going to provide you on your test. I'm going to provide you with the equation that says ME initial equals ME final. The energy in the beginning equals the energy at the end. Now, remember that mechanical energy, as we stated a minute ago, if we look back up, mechanical energy is really potential and kinetic energy together. So what I'm going to say is the following. I'm going to say, all right, well, this is just the kinetic energy and the potential energy in the beginning. And over here, this is the kinetic energy and the potential energy at the end. So, if you know this formula, which you're going to be given on your test, and you know that mechanical energy is simply kinetic and potential together, you're just going to substitute in. Now, sure. Now, what we also know, is the formula, or are the formulas for potential and kinetic energy from section 5.2. So we did 5.2 previously, so we can lead into this. Now, what was the formula for kinetic energy? Kinetic, green. mv squared, very good. And potential energy?
It's mass times gravity times displacement.
Good, times the height, very good. Displacement. Now, if I'm talking about this initially, here's what I'm going to do. I'm going to put a subscript here for vi, and a subscript here for yi. Yi means the initial height. Vi means the initial velocity. Everything else we know, mass and gravity. On the right-hand side, it's the exact same thing. It's the exact same thing. Instead of I, we put at for final. Now, the one thing that we do have to also think about, and this is where the problems become intuitive, is if we have a spring involved in the problem, what was our formula for potential energy of a spring, or elastic potential? Tristan? The units of K are N over M, that's correct, but look for PES. Look for your formula PES. What does it say for that?
Potential energy.
Potential energy. What was our formula for the potential energy in a spring? 1/2 kx squared.
Wait, there's another.
So think about this for a second.
I like
You
memory.
take a spring, you compress it. It has potential to do what?
Bounce back.
Yeah, bounce back or expand. So it has potential energy. Think about it logically. If you take a spring and you expand it, it wants to go back together. So you're storing of energy when you use potential energy. So if there's a spring involved, so imagine the problem said that there's a mass and it compresses a spring, and then the spring is released. So the mass gets launched. And this is realistic, think about it. It's like a catapult if you think, right? A catapult works that way. You're taking some elastic energy, you're storing it, and then you're releasing it. The catapult launches the object. So you store energy in the spring, and then it's released. If there's stored energy, we need to include that in the equation. So if there's stored energy in the beginning of the problem, so if the spring is stored and the mass is sitting there and then it's released, you would have to put in the very front over here 1/2 kx squared. Again, if there's a spring involved, write yourself a little note. If there's a spring involved in the beginning of the problem, you also have spring. potential energy. Okay, again, only if the problem involves it. Yesterday's lab, did we have a spring in the problem anywhere?
No.
So our equation would simply be what you see in blue here. Okay? Again, if there's a spring involved, you have to add that part. There could also be a spring involved at the end of the problem. It's very rare that you see those problems, but if an object lands on a bungee cord, or if an object lands on a trampoline, then there's a spring involved at the end of the problem. So you could technically also have some sort of 1/2 kx squared here. Again, this would be if there was spring potential energy at the end of the problem. But these two things you see in green are not in every problem. You're not going to think about these always because a lot of the problems we're working on don't have springs involved. So you don't have to worry, so these kind of just go to 0 or they drop off. If there is a spring in the beginning, you put it over here on the left. If there's a spring at the end of the problem, you're going to use it over here on the right. And we're going to do some examples of that in these problems so you can see when the spring is actually involved.
I was gonna ask, like, how would it be set into a problem?
So the problem would say like an object is at rest on a loaded spring or on a compressed spring. The spring is then released and it causes a velocity of this, and then we go into the problem. So right away you'd be told there's a spring.
Okay.
You'd be given the K value of the spring, and you might be told how far it's compressed at the X value. Eric, was that the same question?
No, I was gonna ask, couldn't you just include them in the equation anyways, and then
Sure,
later
sure,
in the
sure,
problem,
sure.
just put them to zero, that way you don't
The
forget.
reason I don't include them is because most problems don't actually have springs involved. So traditionally speaking, these are the main 4 you're going to look at, and then those might drop off also. So if there's no initial velocity, this would drop off. If there was no final height, if the object ended at the ground level, this would drop off. So things do drop off. In the other class, I put all 6, and it actually just confused people more. And that's why in this class, I decided to start with these 4, and then discuss the additional spring energy if it was needed. Okay? Again, it's only if there's a spring involved. And I don't use F and I for these ones, because I don't want to call this XF and call this XI, or vice versa, sorry, because it confuses people as to what X is. Remember, X in this equation is the compression, how much has been compressed. So if the spring is normally, say it's a spring and it's on your car, and springs on your car can be like a foot, okay, you can have a spring that's really long. Now, if the spring is compressed to 8 inches, the compression is 4 inches.
It still has to do with like a distance.
It's again, the distance or the displacement between the original spring and the final compressed. So if the spring is a foot and then it's compressed to 8 inches, well then the compression is 4 inches. 12 minus 8 gives us the 4 inches that it has been squished down. So remember, X is the compression, the actual compressed distance. Now, the last thing I want to discuss is this. If you have this equation, this is idealistic. This is with no friction involved at all. Here's my question for you. If there is friction involved, we want to think about where it's going to come up in the equation. And here's how I want you to think. If I take a ball, say, anybody play softball here? Yeah? All right, take a softball and you were to roll a ground ball or you were to hit a ground ball to somebody. Say they missed it and it rolled out to the outfield. Eventually it'll stop, right? Over time it will stop. It might make it to the fence, but say it didn't make it to the fence. It stops over time. So, the ball was moving in the beginning, and at the end it stops. When does it have more energy? In the beginning or at the end? The beginning, right? Because it's moving, and at the end it's not moving. Where did all that energy go? Friction. Friction slowed it down. So here's what I think about it. If I have this kind of a problem, I have a whole ton of energy in the beginning, and I have no energy at the end, because this object isn't moving anymore, right? So if I have all this energy in the beginning, and there's an equal sign here, it needs to balance with something. So you know what we do when friction is involved? We put at the end here, we add on this thing called Q loss, which means just energy loss. Q is energy. So at the end of this equation, if there's friction, so write yourself a little note. If there's friction, you can write the equation like the following, and I'll show you. See this line right here? Take this line right here, and if there's friction involved, put plus Q loss at the end of it. Okay? Again, all you need on one side, again, Q is the loss of energy due to friction. It's the heat energy that you lost to friction. And we put it on the right-hand side over here because of the fact that we lose energy so that there's no longer a balance between the beginning and the end. Now, to be very clear, put absolute value around this because it can get confusing with your equations later on. This is always going to be a positive quantity at the end there. Okay? Again, we're going to look at an example. We're going to get to that example tomorrow. Today's example are going to be about changing height and velocity. Tomorrow examples are really going to be about springs, and then we have two laws. If there's some sort of friction, and we know how much energy is lost in friction. Okay? Any questions on this? So again, our general thing, our general equation is right here. From that equation, we write this. If there's heat involved, or friction, we add this at the end. Then we go into our next equation, where we actually replace all of these values. Replacing all of them with equations here. Now, if there's a spring involved, if there's a spring involved, we have to include the spring potential energy at each end, or at one end or the other, depending on where the spring is. So the idea is this, and the reason I said this is easy is because this is all you're going to do for every single problem. You literally look at the beginning, look at the end, and say, what are the energies at each spot? Now, once you've done that, you can plug in all your variables and solve for whatever you're missing. Let's take a look at an example of this. And this is going to be a conceptual example first, before we get into real examples. Think about a pendulum. What is a pendulum? I'm going to explain to the class what a pendulum is. Good. That's a very good definition. A thing or a mass that swings back and forth about a fixed point. And I like that definition. Okay, so we have something like this.
They're always in people's offices.
Those spikes are.
Okay, let me explain. This means there's a ceiling there, or there's a wall. You ever see something like this, where there's a wall, and there's a beam coming out of the wall, and there's a force acting down in the beam? That's how you draw a wall. It just means some surface. Okay, so when you see these little dash marks there, that means some surface. All right, now, a pendulum swings back and forth. It oscillates. You want to write that word down? Oscillates. A pendulum oscillates, which just means back and forth motion. Now, when the pendulum is at the top of its path, and it's at rest, so somebody's holding this pendulum here, and then the person lets it go. Who has a lanyard with them today? Anyone have a lanyard? I think I asked this one other time, didn't I?
Left mine at
I
home.
think I did. No one had a lanyard.
Left my lanyard at home.
No one-
You used my keys because I have like
What
a
did I use
leather.
last time?
I have a leather thing on my keys.
Do you have it again or no?
No, they're in my locker. I
Yeah.
have my keys.
Who has
Well, you just need like a string.
I need a string with something you got together. That's all I need. That's something that I lanyard.
What is this? Camp?
I have a rubber stretch.
Alright, this is fine. This is fine. Alright. So imagine this is the pendulum. This is the bottom of the pendulum down here. Okay?
Oh.
And you can see it oscillates back and forth. Relax yourself, sir. Now, if you take the pendulum and raise it up to a certain height, it's going to want to fall downward. Now, when the pendulum is extended to its actual height up here, it's not moving, it's stationary.
Use that.
You let go of the pendulum and then it starts to drop like this. It hits the bottom and then it comes back up. Then it goes back down and so forth. Now, at the top here, doesn't it pause for a second? Think about an object when you toss it up. What happens at the max height?
Pause
It
is
stops. Relax.
No.
Now, at the max height here, it's going to stop. So is there any kinetic energy there? No, there's no kinetic energy. So right here, the kinetic energy is 0. But it has potential energy here. Okay, it has potential energy. Now, if I consider this to be the ground, okay, that's the ground now. When this object, or this pendulum, starts to swing through its motion at the bottom, what kind of energy does it have?
Draw the line.
Potential. No kinetic.
Surface.
Oh,
Draw the surface line.
sorry, it's a surface.
Why is there surface on the bottom?
It's a ground, we can need the lines. I get it though, thank you. So, again, let's make believe this is ground level right here.
Wait, we should be drawing this.
Okay, you can draw it, you can just listen for now, these are just concepts. Now, at the bottom, what's the height if the object is at the ground level? What's the height going to be? 0. So there's no potential energy down here, right? At the bottom. But it has some kinetic energy value. How come I know that? Why do I know this kinetic energy?
Because it has to have some energy, and if it's not in potential, it's all in kinetic.
Okay, that's one way of thinking about it. Good. Because of conservation, it's not potential, it's kinetic. What else? Isn't it moving? moving or motion indicates kinetic, right? So right away, since the object is stationary up here, there was no kinetic. But at the bottom, it's moving. So there is kinetic energy now. So the idea is this. A pendulum is your best example. This is the exact same thing as the skater yesterday. Think about the skater. Remember the skater was doing this? Isn't that a pendulum really? At the top, it was all potential. At the bottom, it was all kinetic. Then it was a mix. Then it was all potential. A mix, all kinetic. A mix, all potential. And it constantly flowed. That's what we saw in that bar graph
No,
yesterday.
wait, isn't the bottom meaning kinetic? Why'd you say mix?
Right before.
Potential, mix, kinetic. Mix, potential. Mix. I'm trying to describe what happens in this region over here.
So that's
This is a mix.
Yeah.
Okay? So that's our conceptual idea of the conservation of energy. It goes back and forth between potential and kinetic. Let's look at an example now, numerically. So imagine you have an object dropped, an egg, we said here, but any object. Your book chose an egg, so you use it. So we're told that initially, time equals 0. The object is at a height of 1 meter.
A numerical egg.
No, a numerical example. Egg falling toward the ground. That's a
Duh,
pose.
stop.
So, the object is at 1 meter, it's being held still. Now, I take the object, this is gross, and drop the object. Somebody chewed up a pen can. So the object is at 1 meter,
Why are you touching
okay?
that?
Whatever, it's on the desk. It's being dropped. So take a look at the initial speed. What's the initial speed here? The initial speed is 0, right? So the speed is 0 because it's being dropped. So what kind of energy does it have right now?
Potential. Zero.
Potential. It has energy because it has height. So take a look. It has height, it has no speed. Therefore, it has potential, and it does not have kinetic. And what's the total energy? It's going to be the same as the potential, because it's all potential. So the potential is 0.74 here, so the total is 0.74. Now, I drop it, and imagine, if you will, I didn't actually drop it, and it freeze frames here. Now it's moving, isn't it? Because it's got motion.
Yeah.
It doesn't actually freeze. We take a picture. So it's moving down. So it's got velocity now. So that's this next spot here. It has a speed, and it still has a height of 0.95. So it's only moved a little bit. So now it's got potential from the height of 0.70.
It's got kinetic 'cause
But
it's
it's-
moving.
Also got kinetic of 0.036.
Can you call
Now,
it this table?
If, you can just, this is just to get the idea down. We're going to get into numerical or real examples in a minute. What we're going to see is if we add these two and ignore the rounding, I don't know why your book doesn't just round this to 0.04 to make the numbers work out. So if you round this, you're going to get 0.74, the same total energy still. As the object continues to move down, it loses height. So look at the potential energy. What happens to it?
It drops.
It keeps dropping. But what is it picking up?
Kinetic
Kinetic
energy.
energy.
Because it keeps picking up speed. Look at the speed. The speed's going up. 1, 2, 3, 4 approximately, right? And look at the kinetic energy. The kinetic energy keeps going up. But what do you notice about the total energy? It stays the same. It is constant. It is constant. Any questions on this?
Air blowing out from the table.
So basically,
Where?
Under the table?
it's just cold.
I
Wait,
swear.
wait, Mr. Howell, so can we write it down like as
Alright,
time
go relax.
increases, height decreases, and kinetic energy increases as
You could just
potential?
say as an object falls, potential energy decreases and kinetic energy increases. Okay?
Total
So
energy
step
stays
statement,
the same.
step statement was this: as an object falls, the potential energy keeps decreasing because it's going closer to the ground, where the kinetic energy increases, yielding a total constant or a constant mechanical energy in the problem. Okay? All right, let's take a look at an example here. So this is exactly from your lab yesterday, and I did this on purpose. So if you want to flip over to the 4th page right now of your lab, please write this in your notes, but have your lab out also.
I do.
Have the 4th page open of your lab, and we're going to write this in our notes. Starting from rest, and watch what I'm going to do. As I read the problem, I'm going to write down my givens. Starting from rest means what? Relax, relax. VI is 0. A child slides down a frictionless ramp.
F child.
Okay. So is there any Q loss here?
Nope.
No.
No Q loss because it's frictionless. If there was friction, there would be Q loss.
Can you make like a frictionless ramp? Is that
No.
No, he has to be using some Teflon.
Oh, that would still be some friction.
Yeah, but very little.
Very little. Minimal. Almost negligible. If the height of the ramp,
Get a test in.
if the height of the ramp is 4 meters, determine the speed at the bottom.
Y equals 4.
Good. Yi is 4. Initially it's at 4 meters. And then it slides down to the bottom. What's the height at the bottom?
0.
Wait, why are you doing YF?
Again, the initial height, it's a person at the top of the slide, it's 4 meters. At the bottom of the slide, the person has no height, so we know that it's 0 meters. These givens will help me with my mechanical energy equation a great deal. Now, what are we looking for? The speed at the bottom, so we'll call that VF. Okay, at the bottom. So what is our problem? Here's our problem right here. We've got a slide with a student or a person, a child, at the top, and then the child slides down to the bottom, and now the child's at the bottom. That's literally the problem we have here. So the problem is the child is at the top,
That's such a boring ride.
the child starts at rest, picks up some sort of speed, and ends up at the bottom. Okay? Now, relax. A child slides down a frictionless ramp on a skateboard, okay? Now, if we look at our mechanical energies, in the beginning, we have potential energy I plus KEI. That's a plus sign. Equals potential energy final plus kinetic energy final.
Uh-oh, how much
But the
does he weigh?
question is this. First of all, we don't have the mass. So clearly mass is not going to be involved, and we'll see how that works. But notice, VI is 0. So this person is sitting still at the top of the slide. So there's no kinetic energy in the beginning. Because he's sitting still, right? If I'm sitting still like this right now, do I have any kinetic energy?
No.
No. If I start moving, I do. Now, at the bottom of the ramp, does this person have any height?
No, so no potential.
So no potential at the end. So drop those two off, please. That's the initial, right? That's the initial height, which will refer to our initial potential energy.
Right.
But the final height, YF, is 0. So that drops off. All right, let's write equations now.
Lego.
Potential energy is mgy, and we're going to put an I there, because it's initial. Plus 0, I don't care about the kinetic, it's 0, equals 0 potential, and then the kinetic at the end. 1/2 m VF squared. So again, in the beginning of the problem, we have all potential. At the end, we have all kinetic. Just like your lab. What do you notice? What's on both sides of the equation?
Either or.
Mass.
So what happens, Steph?
Cancel.
Okay, so take a look. These problems, if there's no spring involved, don't all the formulas have m in them? So the mass is always going to drop off if there's no spring. If there is a spring, mass doesn't drop off. You should probably write that in the margin. Okay. Remember our equation earlier? Look back at our equation, please. Okay, look at this equation right here that I'm pointing to. This line right here, this whole thing.
But then no spring.
If I look at that equation, everything has m in it except for the spring part, right? So if there's a spring in here, we can't drop off the m's. Because in order to cancel m's, it needs to be in every single term. But there's no m here, and there's no m over here. So if there's ever a spring involved, the masses don't drop off.
You have to keep
But if there isn't a spring, notice everything has mass. So if there's not a spring, you can reduce by canceling all the masses. Okay? And a lot of these problems don't have a spring, so you'll be able to cancel the mass. Now, let's keep going. We want to find the velocity at the bottom of the slot. So we want to say, okay, Gyi equals 1/2 VF squared. How do I get rid of the 1/2?
multiply by 2.
Multiply by 2. Let's try and raise our hands a little more. Equals VF squared. Raising your hand, tell me how to get VF by itself, please, Steph.
Square root both sides.
Yes. And when I take a square root, Steph, how many answers do I really get?
Remove math.
2.
How many?
2.
What are they?
Plus or minus.
Good.
Don't you remove the 1/2 because that's multiplied times m, which you're canceling?
the m's cancel, but the commutative law of multiplication tells me that I can move the 1/2 around. So I could have made this, instead of looking like this, I could have written this as m times 1/2 vf squared, and then once the m cancels, we still have the 1/2.
So that's the answer.
Okay? That's what the answer for velocity is. And look at the first three parts of your lab. On the fourth page, look at numbers 1, 2, 3, 4. That's what you're doing there in your lab. And then at the bottom of that page, all you're doing is doing a bunch of calculations.
So what's GY?
We had G. G's 9.81. YI, what was the height of the slide?
0. Oh, 4.
4 meters. So go ahead and plug in. And this is why I solve algebraically. Because if you try and plug in the beginning, you're going to see that you don't have the mass. You can't do the problems. If you don't solve algebraically here, it's not going to work because you don't have a mass. All right? What do we get? I think it's
8.86.
8.86. Agreed.
Oh, I agree with that. I agree.
That's fine. As long as you got rid of the m's first and then solve by plugging in numbers, that's fine too. But the thing is, you can't plug in the m. That's why I said that. Now that's the velocity, right? What did the problem ask for?
Wait, what is the G? Oh.
The final velocity.
The final what though? Not velocity, it said something else.
Speed.
Speed. What is the speed with regards to velocity? What do we do with it?
It can only be positive.
Yes, very good, Steph. Good memory. It's the absolute value. So 8.86 meters per second is the speed at the bottom. Okay, it's only going to be a positive there because it asked for speed. Any questions on this? All right, second one. Quickly write this down. We will finish this problem before we leave today. We will finish this one. This one is a very short problem. You'll see it. Quietly write it down. I'm going to start talking about the problem in about a minute. Quietly write it.
A pendulum bob.
A bob is the actual object. I should have mentioned that earlier. The object at the end of the pendulum, the mass at the end, the little like, we drew a circle at the bottom. It's called a bob. B-O-B.
We have a pendulum, Gabby.
I had a friend whose name was Bob, and we took physics together, and they always used to joke.
That was a
That's
rough life for
crazy.
me.
No Bobs here. There is a Robert as a senior, but not Bob. Right? Is there a Robert?
Good
No,
eye.
that was
Good eye,
last
Mr.
year.
Hauser.
String.
Oh no, Robbie Rulin. You're right.
Very.
He doesn't go by Bob, though, I don't think.
No, he goes by Robbie.
So, it's released from some initial height, such that the speed of the bob at the bottom is 3 meters per second. So here's what we've got. We've got an example with the pendulum again. It's got no velocity at the beginning because it's released. Okay, so it's being held there and then it's released. It's got some height we're trying to figure out. And at the bottom of its path, we know that the velocity is 3 meters per second. But at the bottom, it's got no height. So the goal is this. The goal is this. Well, the goal is clearly not there because I didn't write it down. What is the initial height of the bob? That's what we're going to do first. I don't know why it's not there. Something weird's happening.
Weird just went down.
It's in my notes, but it's not on there. What is the initial height of the bob? That's the first part we're going to ask for.
Well, let's figure it out.
Good, good.
Okay? And then part B, at what height will the kinetic and potential energy be the same? Okay? So we're finding the height first, and then figuring out at what height will the potential and kinetic energy be equivalent. So, before you even begin this problem, this is where you have to use your intuition. Don't do the whole problem again. The last problem we just did was a skateboarder doing this, right?
Word.
Isn't that the same thing here?
Yeah, swear.
We have no velocity initially, we have no height at the end. It was the exact same thing as the skateboarder. We have some initial height, nice catch. We have some velocity at the bottom. So this is the exact same problem. It's the same thing. So please, go ahead for part A. For part A, and already, you can just go ahead and write your equation. We had an equation last time that simply said GYI equals 1/2 VF squared. When we cancel the masses, this is the equation we
No,
have.
I thought it's V
Sit.
plus or minus.
Relax.
Oh.
When we cancel the masses in the last problem, this is the equation we had. We then solve for V, but I don't care about that because we're not looking for V in this problem. We're looking for YI. Can I scare you? I'm sorry. What was that face? Oh.
Did I scare you?
Sorry, I thought I talked too loud. You like that. So this was the equation we had before we solved for VF. Now, this holds true for this example because it is analogous. It's the same thing. A skateboarder doing this is the same as a pendulum doing this. It's oscillating back and forth. So for this problem, we want to find out the height of the pendulum. So solve for YI. Divide by G. Okay? Which you can write as, how can I write this? I could just write this as the following. Instead of putting a 1/2 in the numerator, if I take something and multiply it by 1/2, it's the same thing as dividing by 2. So I could write this like this instead, just to make it
That's
easier
what I
on
got. That's exactly what I got.
But this is what I would use for my equation. Okay, it's the same thing as this. You can use either one. Now, velocity at the bottom was 3. So this is going to become 3 squared over 2 times 9.81. Which will give us
9 over.
9 over 19.62.
Why don't I stop getting these answers right? I don't know.
Which will give us a height, initial height of the bob of 0.459 meters. Okay, now, that's the first part. The second part, let me pause for a second, make sure we're all clear. Look up when you're ready. Finish writing and look up, please.
Wait, where are they given?
In the problem. Go back up to the top. Given right here. Given here. Another given right here. Those 3 circle parts. So, the first part said find the height. We got a height of 459. The second part says at what height will the kinetic and potential energy be the same? The same. You need to use intuition here, not math. Tristan, you said something before. What did you say? At what height? I heard you say something right away, and you had the right answer.
You're trying to find
In the middle. What does the middle mean?
the average.
Average, kind of. Okay, middle, median, average, right? What can I think about here? How much energy, or what kind of energy does the bob have in the beginning? What kind? Everybody. Potential. And it's all potential. Let's make believe, hypothetically, that there's 2 joules of potential energy in the beginning. What is half of that? 1, right? So for the kinetic and potential energy to be the same, it would have to have 1 joule of kinetic and 1 joule of potential. Because 2 is never going to change. Remember, the total energy in the beginning, relax ladies, the total energy in the beginning, you're not focusing, come on. I know what she was doing, don't do that, Annie. The total energy in the beginning is consistent throughout the entire problem. So if you start the problem with 2 joules of potential energy, then at the bottom you have 2 joules of kinetic energy. Then you have 2 joules of potential. Then 2 of kinetic, and it goes back and forth. So the only time that they're going to be equivalent is when they each have half of the energy. Is that clear? They each have half energy. If you start, if you start here with potential energy of 2 joules, at the bottom all the energy is kinetic, and it must have 2 joules.
So in the middle?
Okay? So, don't back up here guys, we're almost done. So if there's a possibility of there being an equivalent amount of potential and kinetic energy, it needs to each have 1. Because the total is always going to be 2. So if at some point in time the kinetic is 1 and the potential is 1, then we have a balance. Now, that's going to happen when there's half of the potential energy of the original. So
that would be in the middle.
listen, so what you're going to get here, if there's going to be half the potential energy of the beginning at the point that we're looking for, it has to have half the height. Remember, potential energy is mgy. For this to become suddenly 1/2 of it, it's like saying mg 1/2 y. That's what it's really doing. These are the same things. for this problem to suddenly have half the potential energy like here, it really means that it has half of the height. So the answer for part B is just half of whatever your part A was. So the total energy, so the problem had a height of 0.459. So when will they have the same amount of kinetic and potential? Half of that. So whatever half of that is, 0.2295. 0.2295. Take the answer, the actual height of the pendulum, half of that will give you 0.2295 meters. This is the height when we'll have the same amount of both potential and kinetic energy. Work on your lab tonight, finish it up. You're also welcome to start the next set of problems. Okay, there's some homework out that's not going to be due until Friday. You can start it tonight if you'd like to. There's also the next homework. There's also the next problem set that's due in about 12 days. I recommend that you get started on it at some point soon. Relax, relax. Anybody else have a supplemental assignment for test 4 for me? Have a nice day, Jones. Besides Gabby, I know you told me already.
Have a nice day, Mr. Howell.
You too, Erica.